So thank you so much, everyone, for coming in, and thank you so much, Morgan, for the invitation. Also, my apologies that I couldn't make it to the first couple of days teaching requirements in the this quarter, so I couldn't make it, but I'm very excited and looking forward to the rest of the talk. So, all right, so my talk today is on, so one of the things that I've been trying to do over the past couple of years is trying to understand a certain family of parabolic PDEs and their connection to optimal transport, and slowly morph that into understanding if there can be potential applications of those families towards generative modeling, and do they offer a different perspective to generative modeling than what is out there. I'll start off by saying I'm not claiming anything that this is better or worse. I'm just saying this is different, and hopefully with further exploration, one can come to a consensus on whether the perspective that I'll provide today is useful or not. All right, so the talk is, as mentioned, it's about generative modeling perspective on parabolic via parabolic PDEs. So just maybe some basic notation, because I'll kind of borrow some of this in the subsequent slides as well. So this is just the basic definition of the Wasserstein distance. So I'll pretty much always assume throughout this talk that I'm calculating Wasserstein distance between distributions with positive densities. So I'm just writing it as e upon negative f and e upon negative g. Pi here is the family of couplings between which preserve x and y marginals at e power minus f and e power minus g. And this is the standard square delta loss function for the squared Wasserstein distance. So as we all know pretty much that the optimal coupling here, since I've assumed positive densities, that typically will be concentrated around the graph of a function. And that function is quite a structured function. So that is given by the gradient of a convex function. Here I'm writing that convex function as p infinity. Now, with this in mind, for the rest of this talk, I'll call gradient of phi infinity to be the optimal transport map. That takes you from e power minus f to e power minus g. If there are any confusions about the direction, I'll clarify as we go along, like, what the optimal transport map is from and where it goes to. Right,
just for a quick question, because you said they're positive, so you mean like they're positive from all party, right?
It can be compactly supported, but if it is compactly supported, during a later part of the talk, I'll need some boundary conditions on the compact support to make some PDEs work. But yeah, for the time being, maybe it's okay to vaguely assume that there is an underlying, let's say, domain, could be RT or could be a compact set where this has a positive mass, fully positive mass, yes. Right, yes. So I'll also use the push forward notation here and there. So the push forward notation is basically telling you that typically it will look something like this. Gradient of phi infinity pushes e power minus f to e power minus g, which means if I were to sample x from e power minus f and I pushed it through gradient phi infinity, then gradient phi infinity of x will be distributed as e power minus g. There's a standard push forward notation. I'll probably throw it in there every few slides or something. All right, so this is just a basic setup. So the optimal transport map is a map that takes you from one distribution to another. And this already has a bit of generative modeling feel, right? So you can imagine that if one of the distribution, let's say the distribution that you are going to, like e power minus g, if that is a complicated thing to sample from, and if you have access to the optimal transport map from something simple like a normal, let's say e power minus f is normal, if you had access to the map that takes you from normal to this complicated distribution e power minus g, you could just sample from the normal, push it through gradient phi infinity, and then you'll be able to sample from this complicated distribution. So there is an underlying interpretation of generative modeling already in the framework of optimal transport built in itself, right? Now, I'll use the sort of roughly speaking vague terms target and source, or sometimes target and reference, to denote these probability measures. So I'll use the target probability measure as e power minus g, which should be viewed as something complicated, and the source or the reference one as e power minus f, which is to be something which is easy to sample from. Now, I've split the generative modeling aspect or generative modeling algorithms maybe into two parts. So one, I'll describe a class of algorithms as which are maybe slightly easier to sample from, and another class of algorithms which are maybe slightly easier to learn from. So what do I mean by slightly easier to sample from? So if you look at like adversarial networks, they'll typically, what they'll try to do is learn some transformation that take you from this maybe the easy distribution like a normal, which here is e power minus f, to a more complicated distribution like e power minus g. It doesn't always need to be the optimal transform map that we'll try to approximate. Sometimes it will just model it through some neural network or something, but it will try to capture some transformation that is taking you from an easy to sample distribution to a complicated distribution. Now, if you had access or if you had estimates of that map, now sampling is just a one-step procedure. You just sample from a normal, push it through this estimated map, and you get samples from your target distribution. But the optimal transfer problem is inherently uncoupled. You don't know which x corresponds to which y, which makes learning this map much harder than learning a regression function, for example, where x and y are coupled, right? We know which x corresponds to which y. In optimal transport, we don't necessarily know which x should be matched to which y. So in that sense, learning this map directly with kind of uncoupled data is computationally challenging, obviously, and there are challenges at the rate level as well. So an alternative approach is to do something sequential, which is you're kind of trying to slowly build up to a transformation that gives you a path from e power minus f to e power minus g. So many of the flow-based or diffusion-based methods, depending on how you look at them, will essentially try to slowly move from an easy distribution sequentially to progressively more and more complicated distribution, reaching to maybe your target distribution eventually. So these sort of algorithms which are slowly building up, typically they will build up in a way so that the successive probability distributions that they will generate are quite close, but then they will differ in the first order term. So typically some score function will show up in the first order correction term, and once you can estimate the score function, you have a progressive way to build from one distribution to another, and then you can compose all these transformations to get something that you want to eventually get at. So a common theme in many of these approaches is that you are particularly if they're flow-based, is that you learn these transformations slowly, progressively across time, and then eventually you kind of glue these transformations together, maybe by composing them, or if you're generating samples, you could also kind of generate samples sequentially from these small, distributions, and then eventually get to the distribution that you are targeting. So here, remember, since we're gluing things together in some ways, you're not really sampling in one step, but since we're learning things sequentially, it's slightly easier to learn. You can learn them through the score functions. Learning score functions, there is a lot of tools currently at hand how you would learn score functions in this sort of problems. So this is the dichotomy that I'll kind of be focusing on, that there are a class of algorithms which are trying to learn this transformation in one step, which I'm calling is, let's say, easier to sample from because you can just do a one-shot sampler. And there are other classes of algorithms where the transformation is easier to learn. You are progressively learning it, but they may be slightly harder to sample from because you have to kind of cycle through time. So the one of the goals of this, or one of the motivations that we had while trying to understand whether parabolic PDEs can be useful for sampling is that can the parabolic PDEs, and I'll describe the family of parabolic PDEs that I'll be interested in, can they kind of combine this notion of ease of sampling with ease of learning, in the sense that can they be used to still do something which is one shot, in the sense that even though you are sequentially learning the transformation that you are interested in, when you reach a time point t, you are never cycling back from 0 to t. You are just looking at whatever happens at time point t, and that is your transport, or that is the transformation that takes you from the easy distribution like a normal to the hard distribution, let's say whatever complicated e power minus g you have. And then the sequential aspect should be such that the updates going from time point, let's say t to t plus 1, they should be learnable from reasonably nice score functions, which can be done like you would do in a standard diffusion model. So roughly speaking, that is one of the motivations, that is there can parabolic PDEs be used to combine the notions of, let's say, one-step sampling and sequential learning. As I was mentioning, so this one of the sort of flow-based one of the sort of flow-based PDEs that exists, the Fokker-Planck equation. I'll use it as a baseline for comparison in a later slide as well. So I thought it's not a bad idea to include it here. So for example, if you look at this differential equation, then as t goes to infinity under, let's say, appropriate regularity assumptions, you can show that as t goes to infinity, the solution of this equation converges to your target, e power minus t, which is potentially something complicated. So if you were to discretize this in a very naive way, you would just discretize this equation directly, right? This has a reasonable form. You can just take this equation, discretize it, and you can get the small time distributions, nu 0, nu epsilon, nu 2 epsilon. Think of epsilon as something small. So the way to now go from nu 0 to nu infinity would be taking all this small transformations that you've learned to go from nu 0 to nu epsilon, epsilon to 2 epsilon, and so on. And then you can eventually compose all these transformations, as I mentioned before. Now, one of the other issues when you are sort of taking compositions of such transformations is that even if all these small transformations are optimal to go from nu 0 to nu epsilon, then nu epsilon to 2 epsilon, compositions optimal transpose structure is not preserved through composition. So even if each of these maps are optimal to go from these 0 to epsilon or epsilon to 2 epsilon, if you compose two of them, whatever you are getting is not the optimal transport map from nu 0 to nu 2 epsilon, because composition doesn't really preserve the optimal transport structure, right? So again, you may be saying that, well, I don't really care about preserving the optimal transpose structure, but for the purpose of this talk, I will. I'm also interested in making, or at least making sure that in the limit, if I were to run this algorithm long enough, then the transformation that I get should eventually correspond to the optimal transport map, taking me from the easy distribution e power minus f to the hard distribution e power minus g. So as I mentioned, compositions do not preserve the optimal transport structure. So can we generate or can we construct a flow on optimal transport maps which actually recovers the optimal transport map in the limit? So the compositions might not do that. So with these two motivations in mind, the first one being an attempt to sort of combine the one-shot learning property with sequential learning, and the other property, which is to preserve the optimal transport structure in the limit as well, I'll introduce the family of parabolic PDEs that I'm interested in. And this is a very intuitive construction, which again is not due to me, or I mean, this has been around for a very long time. So this is the standard Monge-Ampère equation, which is just saying that if you were to use the change of variable formula on the transformation phi infinity and e power minus f and e power minus g, then the phi infinity, e power minus f and e power minus g will just satisfy this simple change of variable formula, right? The family of parabolic PDEs that I'm interested in is just a dynamic version of this. So the natural way to make this dynamic is you replace the zero by a time derivative. The hope is that as t goes to infinity, the time derivative stabilizes to something which is, like the time derivative kind of goes to zero, and then whatever you have in the left-hand side here, or maybe right-hand side of the next equation, as t goes to infinity, the right-hand side should go to like fx minus g gradient of phi infinity plus log determinant Hessian of phi infinity, and the left-hand side should go to zero. So this is a natural way to kind of make the static equation on the first display above into a dynamic one. So this is the family of equations that I'll be interested in. This is called the parabolic Monge-Ampère. Again, this exists in the literature, has existed for a very long time. And it is known that if you were to look at this parabolic equation, then in the large time limit, it will converge to, or the gradient of this, or let's say you look at the solution of this equation, take the gradient of it, and then see what happens as t goes to infinity. It will actually converge to the optimal transport map that takes you from e power minus f to e power minus g. So the reason for saying this is, if you could discretize this, this parabolic Monge-Ampère equation directly, then that gives you a way to come up with a discretization that at least in the large time limit preserves the optimal transport structure, which taking compositions wouldn't otherwise do. So it's also possible to kind of relate this to a sequence of probability measures, in the sense that this is the phi t. So I only mentioned that phi infinity, the gradient phi infinity will take you from this e power minus f to e power minus g, but this phi t's also have a sort of a similar interpretation, in the sense that if I were to look at the dual of phi t, the Legendre-Fenchel dual, then the gradient of the Legendre-Fenchel dual, if I pushed e power minus g through that, that will generate a probability measure. Let's call that rho t. And you can view sort of tracking this set of functions, or this sequence of functions phi t, is kind of equivalent to tracking the sequence of probability measures rho t as well. So there is a duality between tracking the evolution of this solution of the parabolic PDE to tracking this rho t's, which are just satisfying that equation, which is gradient phi t push forward rho t equals to e power minus g, which you can kind of see, right? Because this, as long as you have a solution to the parabolic PDE, you can definitely come up with a rho t which satisfies that equation under appropriate regularity. All right, so it is known that under, there's a lot of smoothness assumptions, which I'm currently not getting into. You can actually show that. And so here I've been a bit vague on the strong convexity. Actually, you don't need strong convexity both ways. Actually, I did not put strong convexity, only on the phi infinity, so that's fine. Yeah, so under some regularity assumptions, what you can show is that this corresponding equation admits a unique solution or a unique smooth solution, and as t goes to infinity, the gradient of this solution will converge to the optimal transport map, right? So this is kind of the motivation why we kind of cared about trying to understand this equation or a solution of this equation, and trying to see if that can be used in generative modeling in some way, because it, at least in the large time limit, recovers the optimal transport map. And also you can imagine that, like, at every point D, this also has a optimal transport structure in the sense that it will push forward the sequence of measures rho t to e power minus g. So gradient phi t is actually the optimal transport map that takes you from rho t to e power minus g. And it can also be shown that as t goes to infinity, this rho t's are kind of converging to your e power minus f, which is the simple distribution. So in some sense, these rho t's are converging to the e power minus f, and gradient phi t accordingly is converging to the transport map from e power minus f to e power minus g. So yeah, I'll not discuss too much about the convex conjugate because this is very local to this slide. I just wanted to highlight here that the discretizing this flow is kind of like inherently different from how you would probably view a diffusion model, in the sense that here what we are trying to track is, we are not trying to track the transformation that takes you from a probability distribution to the next probability distribution to the other one, and so on. We are not tracking transformations across successive probability distributions. We are tracking transformations from every probability distribution to a fixed probability distribution. So this is a difference from what flow-based models would do. They would target transformations from rho 0 to rho epsilon, epsilon to 2 epsilon, to epsilon to 3 epsilon, and so on. But what discretizing the parabolic Monge-Ampère does is basically it just directly operates on the space of transport maps instead of operating on the space of probability measures. So we're just tracking the evolution of the maps, not tracking the evolution of the probability measures that are lying here. So just there's a philosophical difference as well in how this discretization operates as opposed to how maybe something flow-based would. Yeah, so I think I already mentioned this. And also there are examples that you can construct for which the parabolic Monge-Ampère equation, if you were to study how it converges to its equilibrium, it's actually faster than what the Fokker-Planck will work, right? So here's a very sort of simple example. So let's say you have both your reference and your target to be a Gaussian. So your starting point or the source, this rho 0 is normal 0 identity, and your target is normal 0 theta. And I'm taking the reference, which is your e power. So rho 0 is basically the starting point of your algorithm, the initializer of your algorithm. And the reference, meaning the e power minus f, I'm taking it as normal 0 sigma. And I'm assuming for convenience, technical convenience, that sigma and theta commute. Otherwise, it's a bit messy to work out things in closed form. And I'm also assuming that everything here is invertible. In that case, what you can show is both the Fokker-Planck and the parabolic Monge-Ampère will admit Gaussian solutions, which is not unexpected. And if the sigma and theta align in a certain way, so sigma inverse theta, I've assumed everything is commuting. So typically what you will get here is sigma power minus half theta, sigma power minus half. The operator norm of that, if that is smaller than 1, what you can show is that if you look at the variance that is coming out of the Fokker-Planck, and if you look at the variance that is coming out of the parabolic Monge-Ampère, both of them should eventually converge to sigma. But if you look at the rate at which they converge, then as t goes to infinity, you can see that the convergence of the Fokker-Planck kind of happens at a slower rate, as opposed to the convergence of the parabolic Monge-Ampère. Or did I write it the other way around? Check. T goes to infinity. Yeah, so this is the denominator is smaller, the numerator is larger. So yeah, that's. So there are also examples where studying this new system of this new discretization or the parabolic Monge-Ampère will give you faster convergence in maybe simple examples like the Gaussian as well. So because of all these reasons, we kind of thought that it's not a bad idea to look at this family or a different family of or this family of partial differential equations and see if they can be, or you can prove some stuff about how you can discretize them, at least time discretize them. And just to summarize what the reasons were for why we are looking at this parabolic Monge-Ampère as opposed to maybe a traditional diffusion model or some other flow-based generative model is, just to summarize here, is that so we split it up initially, that there are examples which are maybe hard to sample from and easy to sample from, and there are algorithms which are harder to learn and easier to learn. So obviously you don't want to use an algorithm which gives you a hard sampler as well as a hard learner. So you probably want to avoid that. Generative adversarial networks give you one-shot sampling, which is what we are calling like easy samplers, whereas they are technically harder to learn just because things are no longer coupled as opposed to maybe in a simple regression model. In diffusion-based models, it's much easier to learn, or at least there are now quite standard algorithms that will help you learn these code functions and so on associated with diffusion models. But you have to kind of, in some ways, cycle through the diffusion to be able to sample from it eventually. So they are what I'm classifying here as maybe harder to sample from, but easier to learn. What we are trying to establish or trying to understand in terms of the parabolic Monge-Ampère is, can it combine sort of the best of both worlds? In the sense, can it be something which is easier to sample from and also reasonably easy to learn? So this is one of the motivations. The other motivation, as I mentioned before, is discretizing the parabolic Monge-Ampère up to a large time t potentially takes us close to the actual optimal transport map from e power minus f to e power minus g, which taking compositions in flow-based models won't do. And finally, as I discussed in the last slide, the parabolic Monge-Ampère can actually be faster, at least compared to the Fokker-Planck in some extent. So these are kind of the main motivations why we started trying to understand how the parabolic Monge-Ampère behaves and how it can be discretized, at least discretized in time. So yeah, so the goal of this talk is basically to study two particular discretizations of the parabolic Monge-Ampère, one which I find particularly fascinating because I could never foresee a connection between one of the algorithms and how it connects to parabolic Monge-Ampère. The other is probably more standard but still has interesting geometric inputs. So yeah, I'll just pause here to make sure that, so this is pretty much the takeaway from the first, I don't know how much, yeah, maybe 10 minutes of the talk. These are the main reasons why I'm trying to understand or trying to study this new family of partial differential equations. Just pause here if there are any questions. All right. All right. So the first discretization that we'll study here is through the Sinkhorn algorithm. So the Sinkhorn algorithm is a very popular algorithm that is used in optimal transport, so one of the beauties of the Sinkhorn algorithm is that if you look at the parabolic Monge-Ampère, it has all these gradient terms and Hessian terms sitting there in the update step. I'll describe what the Sinkhorn algorithm is, but the Sinkhorn algorithm really doesn't have a direct gradient or a direct Hessian in its computation or in its update step itself. So that is one of the reasons why I kind of found quite fascinating that still the Sinkhorn algorithm, at least in a suitable scaling, recovers the parabolic Monge-Ampère. So that is what we will discuss in the first kind of discretization in this talk. So we already discussed what the Wasserstein distance is, so I'm not going to repeat that. So just motivate how the Sinkhorn algorithm arises. So the Sinkhorn algorithm arises initially to kind of ease the burden of computing the optimal transfer problem, because it is because the solution of the optimal transfer problem is quite degenerate. So you kind of want to relax or spread out the optimal coupling in some way. And one way to do that is to put a penalty on the objective function itself so that you don't put mass, or you force the optimal solution to be something which disperses and not put all its mass on the graph of a function. So one way to do that is to put a penalty on probability distributions which are very degenerate. So a way to measure degeneracy is the entropy function. The entropy function is obviously large if, let's say, your distribution is very degenerate. So for example, in a Gaussian distribution case, if let's say your sigma goes to 0, then you know that the entropy will diverge. So that is, so that shows you that if you are putting an entropy penalty, then it will discourage the optimal coupling to be something which is degenerate. So this is the standard sort of entropic optimal transport formulation, which is that you've switched the cost function now. Instead of just being an L2 term, you have added a regularizer which comes through the entropy function. And epsilon is just the regularization parameter, right? And this epsilon will actually play a crucial role in deciding how we decide to scale the algorithm, right? So there has been a lot of extended work on the entropic optimal transport, its characterizations, and how to view this. So I'm just repeating some of the things that, I'm pretty sure most of you already know here. The optimal coupling coming out of the Sinkhorn algorithm has a particularly nice functional form. And if you look at this particular functional form, what is also true is that since this still has to be a coupling, which means that this still has to preserve the x and y marginals at the correct e power minus f and e power minus g, this integral constraints need to be satisfied. So if you kind of rewrite this integral constraint, then you get a system of fixed point equations. Fixed point equations involving these potentials phi epsilon and psi epsilon. Obviously, you cannot solve for them in closed form because phi epsilon depends on psi epsilon and psi epsilon depends on phi epsilon. So, but still having this fixed point equation probably immediately motivates a nice algorithm that one could generate just by alternating, starting from some, I don't know, psi 0, going to maybe phi 1, using phi 1 to go to psi 1, and then something like that. That is exactly what the Sinkhorn algorithm is. It basically takes this fixed point system, which comes quite naturally out of the characterization of the optimal solutions of the Sinkhorn algorithm, and it just updates it recursively. That is exactly what the Sinkhorn algorithm is. So maybe just to outline it regardless. So here is just what I described in words. So you are what you are doing here is you are taking, maybe you are starting off with the phi epsilons, phi 0, you are using that to update psi 1, then you are using psi 1 to update phi 1, and then kind of doing the same thing alternately. Right? So far what I've described, if you look at these updates, note that these updates do not involve any gradient computation. And also if you look at the integrals are with respect to these probability measures, right? E power minus f and e power minus g, which means technically if you just had observations from these things, you wouldn't really need to like solve for the integral. You could just average out the integrals by sample averages, and that would give you hopefully reasonable estimates depending on what your epsilon was. So this is a reasonably convenient thing to compute. Obviously, as epsilon gets smaller, you can imagine the variability associated with estimating something like this will get larger. So there is obviously technical difficulties there. But just in terms of an algorithm, one could imagine if I just had observations or discrete observations from e power minus f and e power minus g, we could just feed it into the algorithm quite reasonably or easily. So once you have this potentials, if you remember what the optimal coupling for the entropic problem was, the optimal coupling for the entropic problem, I think I wrote it out here. So that motivates a very natural definition of the optimal coupling at every step of the Sinkhorn algorithm. So basically you take these potentials and just plug it into the same functional form as you have here. So you have the inner product part, you have the f and g part, which are given to you. Just these potentials you update with the potentials at the current step. So here I think the way I wrote it, the natural sort of indexes are k minus 1 and k, but if you just wrote it differently, it would be phi k and psi k. And if you were to just compute the x and y marginals arising out of this coupling, you can always see that the y marginals are fixed at e power minus g. You can just integrate things out and you will see that, but the x marginal will kind of change. So the idea here is that as kind of k goes to infinity, the x marginal will converge to e power minus f as the y marginal always stays fixed at e power minus g. Now I could always kind of flip things around by changing the like, the kind of the order of phi k's and psi k's by messing things up. Then I will get a different coupling, in which case the x marginal will always be preserved at e power minus f and the y marginal will move around, and the y marginal in the limit as k goes to infinity will converge to e power minus g. So it's kind of a classic case of like just alternating updates with the fixed point equation. Here we are kind of tracking like two-step updates. So when you are doing two-step updates, one marginal always stays fixed, the other kind of converges to the target, and it depends on how you write the equation, which marginal will stay fixed. So this is just a basic primer on the Sinkhorn algorithm. So far, I've not discussed how the Sinkhorn algorithm relates to the parabolic Monge-Ampère, which was the goal of the talk, but we'll get to that. So the main thing that we'll show here, or the main thing that we will discuss here, is if I look at now the potentials that are coming out of the Sinkhorn algorithm. So let's say you have this phi k epsilons, and I take the gradient of this potential. So far there is no direct connection between this update step and the parabolic Monge-Ampère. But as it will turn out, that these gradients can actually be in a certain scaling limit we use to approximate the solution of the parabolic Monge-Ampère. So that is kind of the main part of this section of the talk, that the Sinkhorn algorithm, which technically does not involve any gradient or Hessian computation, can still be used to approximate the solution of the parabolic Monge-Ampère. Yeah, so this is the main message, and I'll describe the result in a few slides, but this is what we will eventually get at. Pause. All right. So I think I already mentioned this. So this is just maybe a list of nice things about the Sinkhorn algorithm and maybe some not so nice things. So as I mentioned, for samples, things are good. You can always compute it. There is nothing weird about just the computational part of it. And there are also faster computation techniques, some online algorithms which have been studied extensively, and like a lot of work has been done on this. So yeah, I'm definitely not adding anything new here. Also, as I mentioned, although the updates of the parabolic Monge-Ampère, this equation which I wrote out before, involves a lot of gradient and Hessians, the Sinkhorn algorithm does not involve any of that. But the bad part also is that the Sinkhorn algorithm is if you are choosing epsilon to be small, which you will need to do in the scaling limit, there are a lot of instabilities, that at least computational instabilities, that will come up for sure. And that typically comes in because of this exponential term, like e power 1 over epsilon. If your epsilon is small, then this can really mess things up. So there are also some regularizations which people have tried in the literature. Although I'll work with this specific form, I should add the caveat that I will take epsilon going to 0 for theoretical reasons. All right, so in the next part, before I show you what the exact result is, remember I've been vaguely using the term scaling limit. So what do I mean here? So what we mean here is, for scaling limits, you not only need to take epsilon going to 0, you also want to make sure that you run the Sinkhorn algorithm long enough. If you just run it one step and take epsilon going to 0, you won't get anything meaningful, right? So the idea here is, how do we scale the number of iterations of the Sinkhorn algorithm along with the regularization parameter of the Sinkhorn algorithm? And that comes from very natural considerations associated with gradient descent or scaling limits of usual gradient descent. So for example, if you look at the updates of the Sinkhorn algorithm, and this is some sort of a complicated equation, which we don't need to get into like the specifics of what each of these terms mean. But typically on the right-hand side, there is some derivative evaluated at iteration k. And on the left-hand side, you have difference of two things. And the difference is at time point k plus 1 and k. So this is a explicit form for the Sinkhorn algorithm that one can write out for a particular function h epsilon, which is quite implicitly defined. So I'm not writing it out exactly here. But the main sort of point that I want to stress here is that this sort of updates should kind of push you towards, maybe there is some underlying gradient descent or something like that happening here. It's kind of updating something very close to where you would update a gradient descent. But there is a subtle difference here. So in gradient descent, you typically have the step size sitting on the right-hand side. So it's typically like epsilon times the whatever gradient of f or something like that. Here you don't have the epsilon sitting on the right-hand side. The epsilon is kind of embedded in a nonlinear fashion within this h epsilon function, which needs to be kind of isolated and pushed to the right-hand side in an appropriate limiting sense. So this is not a typo. This epsilon is there. It's just sitting in an implicit way in this h epsilon operator. Right. So this is probably should be reminiscent of usual gradient descent up to this missing epsilon, which as I mentioned before, is sitting on the left-hand side. And for usual gradient descent, we know the correct sort of scaling limit is, if you were to choose your number of iterations to scale roughly like 1 over epsilon, then as you take epsilon going to 0 and number of iterations accordingly going to infinity, because number of iterations is t over epsilon, then this has some nice sort of scaling limit behavior, and you can track the evolution of this through this continuous system given by this continuous system, which is given by ddt of xt or x tilde t is negative gradient of f at x tilde t. So this is there's some standard results here. I have a reference up there, but the main thing that I want to take away from here is that this scaling, where the gradient descent kind of has a non-trivial limiting behavior, is also the scaling that we will use to analyze the Sinkhorn algorithm. And the motivation comes from this sort of an update step. So what we will show eventually is that if you scale the iterations of the Sinkhorn algorithm to be some, let's say, t over epsilon, where epsilon is the regularization parameter of the entropic optimal transport problem, then in that scaling limit, the Sinkhorn algorithm approximates the solution of the parabolic Monge-Ampère. So you can use the Sinkhorn algorithm to discretize the parabolic Monge-Ampère in that scaling limit. That is the sort of main takeaway here. It's okay. 20 minutes. 20 minutes, okay. So, all right, so now going to the approximation. So just to recall of the parabolic Monge-Ampère, I will, so phi k's and chi k's are the potentials from the Sinkhorn algorithm whose gradients we are using to approximate the solution of the parabolic Monge-Ampère. The main result here is that if I were to look at so this first term here is the gradient of the potentials from the Sinkhorn algorithm. The next term here is the solution of the parabolic Monge-Ampère. If I were to take their difference, and if I were to scale that by epsilon, as epsilon goes to 0, you can write out what this limit will be with appropriate initialization of the Sinkhorn algorithm. So this basically tells you that under the scaling limit, when your k is t over epsilon, the solutions of the Sinkhorn algorithm converges to the gradient of the potentials from the Sinkhorn algorithm converges to the parabolic Monge-Ampère solution at a rate which is like epsilon. So it goes to 0 at a rate epsilon, up to constant epsilon. And this is reasonably tight because there is a limit here. So this is not like, the limit is not 0. So there's a limit here. It doesn't really go faster than epsilon. And what you can also show is that there is an underlying Gaussian process approximation that also happens for the probability measures associated with the Sinkhorn algorithm. But since the focus of this particular talk is more on the approximation of the potentials from the parabolic Monge-Ampère, I will not discuss so much about this underlying Gaussian process. So yeah, you can kind of also track the evolution of the Sinkhorn algorithm through an underlying Gaussian process, but I'll just focus more on the first display here, which is that the Sinkhorn algorithm, the gradient from the Sinkhorn algorithm can be used to approximate the parabolic Monge-Ampère. So this is the first discretization, and let me also make sure that I mention that this is obviously not the first result in the area. Probably one of my most favorite papers is this paper by Berman in 2020, which first shows that the Sinkhorn algorithm, at least the potentials from the Sinkhorn algorithm, not the gradient, the potentials can be used to approximate the potentials of the solutions of the parabolic Monge-Ampère without the gradient at order epsilon scale. And in that paper, actually, it also talks about the approximation of the gradient. The approximation rate for the gradient that is derived is order square root epsilon, which is kind of what you would expect from a reverse Poincare type inequality, which may not be tight, but the argument used in the Berman's paper would give you something like order root epsilon. Although he did not use reverse Poincare, but a different argument, but it still gives you a square root epsilon order. I suppose what is happening in the previous result is that we are kind of showing that this rate is actually not tight and this growth is actually of order epsilon. You can actually find out the limit when you scale by epsilon and take everything going to 0. The limit is something non-trivial. So you cannot really get faster rates than epsilon. Previously in a different paper of mine, different paper with me and co-authors, we also showed that we kind of, in some weak sense, we computed the limit of successive time differences of the potentials in the Sinkhorn algorithm, but none of that actually translates into an approximation for the gradient of the parabolic Monge-Ampère. And these results don't really cover what I showed you in the previous slide. And there are also other sort of marginal convergence results that were derived earlier whose rates can be improved if you have this order epsilon convergence of the gradients, which again, I'm not getting into, but some of the previous results can also be improved from the order epsilon convergence that I mentioned in the previous slide. So that's what I was mentioning here. I should mention also that everything that I discussed is only with time discretization. I did not talk about space discretization at all. But in order to get this improvement from square root epsilon to epsilon, I did assume 2 extra orders of regularity on the solutions of the parabolic Monge-Ampère. So previously, the order root epsilon rate was obtained through assuming something like order 4 smoothness. For this, I do need order 6 smoothness. So this is not coming free of cost. There is also some work on space discretization. The rates are not really comparable. I think the rates here are sharper, but since I'm not talking about space discretization here, I'll skip a direct comparison with this little. The only comment I'll make on space discretization is so far not exactly sure how to do it if you have random data, but if you have data which is supported on like a torus and deterministically discretized with some sort of a uniform grid, then you can actually carry forward some of the calculation that I showed you with discrete data as well. Not going to go through all the details, but just so you know that for d-dimensional torus, if your data is supported on a d-dimensional torus, then you can actually do some of the computations that I mentioned before. But as of now, the most general case that we can cover is when there is no space discretization, if you have full access to e power minus f and e power minus g. Okay. All right, so I'll not discuss the proof technique given that I'm a bit short on time. So I'll probably end the first part, the first notion of discretization here, which is that the Sinkhorn algorithm, which is kind of like gradient free, that also helps you to discretize the parabolic Monge-Ampère in some way. So I will skip the particle methods here and probably move on to the other notion of discretization, which is a bit more direct, and I kind of think it's probably the first way of discretization that one might think. Before going there, I should mention that there are also a lot of open questions here. As I mentioned, space discretization, we really don't know exactly how to get tight characterizations with space discretization. Also, this reference distribution, right, which is the one you are choosing, the simple distribution, that does affect the rate of convergence of this sort of a process. So how to choose that in practice so as to optimize over maybe a class of distributions, again, is not really clear. Hopefully, this gives some perspective or different perspective of generative modeling, but we are still kind of doing numerical experiments to see if this is how practically useful this is. So the next discretization that I'll talk about is probably the more like natural discretization, or at least more intuitive one, while the Sinkhorn may be mathematically more elegant. So just a quick recall of the equation. And here I actually cheated a bit just to make the notation consistent with the paper. I actually switched the target and the reference. So previously I said the target was e power minus j and the reference was e power minus f. I switched it just to make the notation consistent, and I got lazy, did not want to change all the notation to the previous one, but conceptually nothing changes. I've just changed the roles of e power minus f and e power minus g for this section. So this is a quick recall of the usual Monge-Ampère and the parabolic Monge-Ampère. So the most natural discretization one can probably think of is just to discretize it like you would discretize any usual gradient descent, right? So you have a time derivative here, which probably means that you just take a time derivative on the left-hand side with some step size. So I call that step size to be eta k. And on the left-hand side, you have this sort of term which you keep it exactly as it is. So your update step will be something like negative f gradient of psi ky plus g times y plus log determinant of diffusion of psi ky, which if you kind of rewrite in the language of probability measures can actually be written in terms of density ratios or log density ratios of score functions. So if I were to write rho k as the probability measure which is obtained by pushing your e power minus g, which now is the reference, through this transformation gradient of psi k, which is the current update. If I were to put that probability measure as rho k, then you can see that, through some algebra, you can see that the natural update step here will basically just be the log density ratio composed with this current iterate and the gradient of that. So it's just a direct calculation that one can do, and just the change of variable formula will show that this is the natural update step. So this is another discretization, probably the more natural one that we can do. And this has the step size in the correct place that you would expect from gradient descent. So this is eta k times the gradient if you push it to the right-hand side. Previously in the Sinkhorn case, this was kind of implicitly embedded in some other terms. So this is, as I mentioned, this is probably the more natural mechanism to do this. And if you look at the update step, this involves this density ratio of your current probability measure and the target probability measure from which, let's say, you have some data from. And now there are already many sort of techniques known to estimate density ratios, log density ratios, or gradients of log density ratios, score function. So for example, if you just wanted to estimate the log density ratio, one of the things that one could do is, since you already are at time point k, which means you have already updated your algorithm up to gradient of psi k, remember your rho k is just the push forward of gradient psi k with e power minus g, which is the reference distribution, which means that if I wanted to sample from rho k, I could just take gradient of psi k, sample as many observations that I want from this reference distribution, and just use this update to sample particles from rho k, right? So once you have observations from rho k, what you could do is you could use these observations. So I just write these observations here. And you could use these observations and couple them with standard sort of score learning techniques and density ratio learning techniques, like the classification trick or the score matching trick. You can use that to learn the score functions or the density ratios which occur here. Right? So this is the kind of algorithmic thing that we use. We don't really compute the score function by hand. We just sample from it and use some of the off-the-shelf methods for learning score functions of the density ratios based on these existing ideas like the classification trick and the score matching trick. I'm not going through the classification and score matching trick. This has been around for a while. So this is what we use. So yeah, I have the algorithms here. There's no point really going through the exact steps of the algorithm. So I'll probably take maybe the last few minutes that I have to tell you what rates one can prove for this new update scheme. Again, everything is time discretized. I'm not talking anything about space discretization. It's only time discretization. So a very simple thing that one could show, and the proof is very simple, you could probably guess how it will work, is that if you now look at the probability measures that you get out of this sort of update step, remember the rho k's that I mentioned before, they will converge to your target at a rate which is 1 over t. If, for example, you took all your rho k's that you've collected up to time point t and took a mixture across all time. So basically, take all the probability measures that you generated from 0 to t, just take the equally weighted mixture of them, call that to be rho bar t, that will converge to your e power minus f at a rate which is roughly 1 over t, which is obviously quite easy to guess that something like this should happen. So there is nothing special here. Now, to get something sharper, I'll need this sort of geometric notion of the Bregman divergence on the space of Bregman divergence of the Wasserstein distance as a function on probability measures. So I call this function g to be half of the squared Wasserstein distance between rho and e power minus g. So this divergence will actually serve as a kind of a local metric to evaluate the convergence of this algorithm, this sort of update step that I mentioned before. So this is just a first, so this is the usual divergence, right? So you have the main term, which is the Wasserstein distance, and then you are just doing a first order correction around some probability distribution rho 1. So this term is basically the first variation of the Wasserstein distance. This has been worked out before. I'm just kind of using that here. All right. So this is the sort of probably the last technical slide of this talk, which is that if you were to use time invariant step sizes, so pretty much everything that we expect in usual gradient descent will happen, modulo one slight caveat. So if you look at the usual regret by using time invariant step sizes, if you were to add up from t to 0 to t, then you will get a square root t rate. If you were to choose adaptive step sizes that shrink with time, then you will get a much faster rate, which is like log t. Typically, to do this improvement, you need some sort of strong convexity somewhere. The important thing here is that to do this, you actually need strong convexity on the reference, which is the easy distribution, not on the target. So this is a kind of a useful property that you are not directly requiring a strong log concavity as a, sorry, I should make it log concave and not convex. So you don't require a, no, I think it's fine because it's on G. So you don't require a log concavity assumption on the target, you only need it on the reference distribution. And then you could use that to kind of get convergence for the last iterate as well, right? Okay, so you have a few more minutes to just discuss this, right? Okay. So just to elaborate a bit on this point, that the strong convexity is not required on the target distribution, but only on the reference, it kind of comes up from a notion of convexity of the Kullback-Leibler divergence, which could be somewhat new, not totally new. So I'll maybe just mention it in passing. So in this whole analysis, there are kind of two things which seem, or at least seem to us, to be a bit different from usual analysis of maybe regret bounds and things like that. So typically, maybe how a regret bound would work is you have your step size, and then you multiply it with a local regret. By local regret, I basically mean, roughly speaking, a regret at time point k. So basically, maybe here something like the Kullback-Leibler between rho k and e power minus f. So this will involve, it will be bounded by, like when you do most of these calculations, there will be a telescoping part and a continuity part. So the continuity part is typically something which is of a smaller order than your step size. So maybe something like square of the step size. And the telescoping part is what will kind of cancel out when you sum up over all your local regrets. So that will kind of cancel out a large chunk of terms. And since the continuity term is already like of a smaller order, that gives you a reasonable handle on your regret bound. So typically that's how things work. Now, the telescoping term and the continuity term in sort of many of these existing procedures will typically, to get these terms, typically relies on some form of a three-point identity. So here is a very basic three-point identity with Euclidean data. So this basically says that given any x1, x2, z, this sort of an identity holds. So you can imagine that like these two terms, you can imagine your x1 and x2 are like xk and xk plus 1. So this part in red is like a telescoping part. So if you were to just add up over k, you will see a lot of the terms cancel out because of this difference term here. And this is the continuity part, because if you imagine your x1 and x2 being xk and xk plus 1, the gap between two successive iterations is like of the order of your step size. When you are squaring it, you get something like step size square. So it brings the size of the continuity term down. So the equivalent sort of identity that we get here, so the main difference, I suppose, here is that if you look at this sort of an equation, the telescoping part and the continuity part, they both have kind of the same distance kernel. It's just the Euclidean distance. If you had a different divergence here, it would involve divergence of the same function. But in the analysis that we had to do in the previous one, the telescoping part and the continuity part correspond to two different Bregman divergences, in the sense that one is a Bregman divergence associated with this Wasserstein distance function that I showed here, and the continuity part involves a different Bregman divergence with respect to a different function g prime. So this is a bit of a geometric difference that is happening here, and beyond the algebraic part, we actually don't have any understanding of why this little geometric difference is arising. And the other sort of thing that is happening here, which kind of explains why we don't typically impose a strong convexity on the target distribution, is that the proof of like getting log t regret goes through a notion of strong convexity of the Kullback-Leibler divergence with respect to the Bregman divergence directly, not with respect to any metric. And this particular notion of convexity only requires strong log concavity of the reference distribution, not of the target, and also strong convexity of a certain Brenier potential. So we typically have the belief through regularity results by Caffarelli that if things are like, if both your distributions are log concave or something like that, then your potentials will have some convexity properties. But the other way around is supposed to be weaker in the sense that convexity of your Brenier potentials is possibly weaker than imposing log concavity on both your source and your target. So we hope that having this notion of convexity being enough to get log T regret might be useful for trying to sample from things which are not log concave. But again, this is subject to maybe practical implementations, which we are currently trying to do. So just to conclude that what kind of I try to motivate here is that maybe there is a reason to consider a different set of generative modeling algorithms which pass through the lens of these parabolic PDEs. And there are different discretizations that one could do, the Sinkhorn algorithm being one, and this the more canonical discretization being the other one. And both have some reasonably nice properties, but there are also a lot of geometric questions that we don't understand. Many of these are quite algebraic at this time point, and hopefully in time we can kind of develop a better understanding of that. So yeah, sorry for the long spiel. If there are any questions, thank you.